All right, so you know how we're always talking about technology pushing the limits? Well, get this.
Okay.
Lasers.
Yeah.
Right? There's making lasers now, these pulses of light, so powerful
Oh, wow.
that for just a split second,
Yeah.
they can actually outpower
Really?
the entire planet's electricity consumption.
No way.
I'm talking orders of magnitude more powerful.
That's insane.
Just for a tiny, tiny fraction of a second.
Okay.
It's crazy to think about, right?
Yeah, that really puts things into perspective, like just how far we've come with technology.
It really does. And it makes you think like, okay, if you can cram that much energy into such a short amount of time, what does power even mean at that scale?
Right.
You know, it's like
We're almost redefining physics.
Exactly.
Pushing the boundaries of what we thought was possible.
And so the immediate challenge that comes up is, how do you measure something like that?
Oh, yeah, good point.
I mean, these pulses are so short, so intense. How do you even capture that accurately?
It's got to be tough.
And it turns out this has been a real head-scratcher in the world of laser science for a while.
I can imagine.
But there might be a solution on the horizon, thanks to some really cool research coming out of the Tata Institute of Fundamental Research in Mumbai.
Oh, interesting.
They've published their findings in Optica, and that's what we're going to dive into today.
All right, let's hear it.
We're going to break down their new measurement technique
Okay.
and why it's such a big deal for the future of lasers.
I'm all ears. You know, for years, these ultra-short, super powerful pulses, they've been incredibly hard to really pin down and measure.
Yeah.
This new method could give us a way to really look into these tiny, fleeting moments of energy.
Yeah.
It could change everything.
Okay, so to wrap our heads around all of this,
Sure.
let's try and picture how extreme these laser pulses actually are.
Okay.
When we say ultra-short, what kind of time frames are we talking?
All right, so we're talking femtoseconds.
Femtoseconds.
Yeah.
Okay.
Now, a femtosecond, that's a quadrillionth of a second.
A quadrillionth.
Quadrillionth.
Okay, so, like, help me understand that.
Okay, so imagine this.
Okay.
A femtosecond is to 1 second.
Mm-hmm.
1 second is to about 31.7 million years.
Whoa. Okay. That is mind-bogglingly short.
Right. It's almost impossible to even comprehend how quick these pulses are.
And then you cram all that energy into that tiny, tiny window.
Exactly.
And, as we said, the amount of energy can be absolutely staggering.
Oh, yeah.
The paper talks about power levels exceeding the entire world's power consumption.
It's hard to believe almost.
By orders of magnitude.
And when they say orders of magnitude, we're not talking about like twice as much or 10 times as much.
Right.
We're talking potentially thousands, millions, maybe even billions of times more.
More than the whole planet uses.
More than the whole planet uses in a fraction of a second.
It's really hard to picture that much power.
It is. And this really marks a turning point in the world of optics, you know?
Yeah.
It's not just about bending light anymore. It's about controlling and understanding these insane bursts of energy,
Yeah.
as the paper puts it. Optics has become a game of extreme power.
Okay, so we've got these incredibly short, incredibly powerful pulses of light.
Yep.
Why has it been so hard to measure them accurately?
Well, one of the big problems is that when these pulses go through anything, any material at all, even the stuff in your measuring instruments, they can actually change.
Oh, interesting.
The pulse gets distorted.
So the act of trying to measure it is changing it.
In a way, yeah.
Okay.
And the more power you pack into that pulse, the worse the distortion gets.
So it's kind of like a catch-22, right?
Yeah, exactly.
The thing you're trying to study is so powerful that it messes with the tools you're using to study it.
Exactly. But it gets even trickier.
Okay.
The researchers at TFAR, they point out that the pulse time profile, it's not uniform across the whole beam.
Wait, so it's not like the whole beam is one perfectly synchronized pulse?
Nope.
Okay.
Different parts of the beam can actually have slightly different timing.
It's more complex than that.
Way more complex.
Okay.
Now, for lasers with less power, scientists might just ignore these little variations.
Right.
But when you're dealing with these super high power lasers, these giant beams, these tiny differences, they become really important.
So you could get different readings depending on where on the beam you're measuring.
Yeah, absolutely. And that can really mess with your data.
Right. It's like if you're trying to measure the speed of a car, but you're only measuring one of the wheels.
Exactly. And that's where this new research comes in.
Okay.
The TIFF team, they've come up with a way to address both of these problems, the distortion and the variations across the beam.
So tell me, how did they do it?
So they used this special instrument Basically, to take snapshots of the pulse at multiple points across the beam all at the same time.
Okay.
It's like taking a panoramic picture, but for time.
Interesting.
The key is a technique called spectral interferometry.
Spectral interferometry.
Yeah, it's a mouthful.
Okay.
Basically, they analyze the colors within the laser light and how they're out of sync to map out the shape of the pulse.
Wow.
But the real innovation here is that they're doing this at multiple points across the beam simultaneously.
Ah, so they're getting a much more detailed picture of the pulse.
A much more detailed picture, not just one average measurement for the whole beam.
And this is important because, as we said, the power of lasers is just going up and up.
Oh, yeah.
They're talking about lasers in the tens of thousand trillion watts.
It's hard to even imagine.
I know, it's insane.
And these lasers, they're going to be huge.
Yeah.
Spread over meters.
So this new technique is essential for understanding these future lasers.
Absolutely essential.
Okay, now, there was another interesting thing in the paper about measuring single pulses.
Oh, yeah, that's a big one.
Why is that so important?
Well, a lot of these ultra-high power lasers, they don't fire continuously. They might only produce a pulse every few seconds or even minutes.
So trying to measure them is like trying to hit a moving target.
Exactly. And the old ways of measuring, they needed multiple pulses to get a good reading.
That doesn't sound very efficient.
Not at all. Imagine waiting minutes between each measurement.
Yeah, talk about tedious.
Right. But the TIFR method, it can work with just one pulse.
Wow.
One shot and you're done.
So they can get all the information they need from a single firing of the laser.
Exactly.
Okay.
Which is huge because it means they can study each pulse individually, even if they're all slightly different.
So they've solved the problem of distortion, they've solved the problem of variation across the beam, and they've solved the problem of measuring single pulses.
Yeah, pretty impressive, right?
What else?
What else is...
Well, the research also talks about using plasma for optics.
Plasma optics.
You see, when you get to these crazy high power levels, regular lenses and mirrors, they can't handle it.
They just melt. Basically, yeah. The material gets turned into plasma, which is like a superheated ionized gas.
Okay.
So scientists are looking at using plasma itself to make lenses and mirrors.
So you're using the same thing that melts regular optics to make new optics.
Exactly. It's pretty wild.
Wow.
But of course, plasma can be unstable.
So it introduces its own set of challenges.
It sure does. And you need to be able to measure and understand those new distortions that plasma creates.
And I'm guessing this new technique can do that.
That's exactly what the TIFR researchers say. They say their method is perfectly suited for measuring these plasma distortions.
So it's not just helping us understand the lasers themselves, it's also helping us develop the tools we need to control them in the future.
It's like a feedback loop of innovation.
It is. It really feels like this research has the potential to change the game.
Yeah. Absolutely.
In fact, the paper even asks a one-shot solution for all ultra-high peak power lasers. And their answer is, that is the promise.
Bold statement.
It is a bold statement.
But do you think they can deliver?
Well, based on what we've talked about, it seems like they're on the right track.
Yeah, I'd say so.
Being able to do a single-shot, spatially resolved measurement of these crazy powerful laser pulses, it solves so many problems.
It gives us a much clearer picture of what's actually happening.
Okay, so let's wrap this up.
Well,
what's the key takeaway here?
I think the biggest thing is that these researchers in Mumbai, they've come up with a way to measure these super short, super powerful laser pulses with incredible accuracy.
Right.
And they can do it in a single shot.
No more waiting around for minutes between measurements.
Nope.
And they can map the pulse across the entire beam.
Yep. Even when dealing with tricky stuff like plasma.
This solves some fundamental problems in laser science and paves the way for a whole new generation of lasers and laser technology.
And for you, the listener, it really highlights how important measurement is to scientific progress. You can't really understand something until you can measure it. And this seemingly small advancement could unlock a whole new world of possibilities.
It really makes you think, doesn't it?
It does.
If we can control and measure these bursts of energy that are more powerful than the entire planet for a tiny, tiny moment, what could we achieve?
It's a good question.
What new discoveries are waiting to be made?
I mean, could this be the key to finally making fusion energy a reality?
That's a question for you to ponder.
It is.
Because the future of lasers, it's looking very bright.
Very bright indeed.
And who knows what amazing things we'll be able to do with them.
Only time will tell. But I'm excited to find out.
Me too.
Me too.
All right, that's it for this deep dive. Thanks for listening,
Thanks for having me.
and we'll catch you next time.
See you then.